Right. Hello students. Today we are going to discuss composite functions, binary operation, types of binary operations, textbook examples. So in part 1 we are going to discuss binary operation, types of binary operations. Part 2 we are going to discuss textbook examples. This is today's work. Before going to our class, just close your eyes, we'll pray. God, kindly provide your knowledge and wisdom to solve our mathematics problems and our daily life problems. Thank you, God. Right, let's move on to the part 1. So, in that binary operation, so bi means 2. So, the operation which was done on two operands is called as binary operation. So, two numbers are a comma b, will everything, and operation binary operation is a star, and now the star means plus minus divided by into so on, like in sets if you go union intersection and so on. So what is exactly binary operation? A binary operation star on set is a function. Yes means you can take capital B capital C also, is a function. Therefore, star S crosses maps S. S crosses means what do you know? That is Cartesian product to S. We denote star A comma B by A star B. That means A is belongs to the S, B is belongs to the S. That implies A star B belongs to S. For every A comma b belongs to S. So this is about binary operation. Star S crosses to S. So if you take A cross A maps A, B cross B maps B, and so on. So we'll take one example so that you can understand clearly. So example 1 here. So the first one it is plus addition, subtraction, multiplication of integers are binary operation on a set of Z or I which relates the elements A comma B of Z. Just take one example. For example, 1 plus 1 is equal to 2. That means A is 1, B is 1. X0 plus 1 is equal to 1. So next we are taking some other integers, that is subtraction. 1 minus 2 is equal to minus 1, and then 1 is multiplied with minus 2 is equal to minus 2. You are observing that all the results are you are getting as integers. Let me check division. So A is 1, B is 2. If I take 1 upon 2, 1 upon 2 is nothing but rational number. It is not possible binary operation. The reason behind that you are finding in all the places integers you got, but in the division you are not got integer. So because of that, so division is not binary operation and remaining all binary operation. So you need to check whether it is binary operation or not binary operation by using like these examples. Okay, some more examples in your textbook. Those are 6 examples are there. Kindly check it so that you can understand clearly that. So this is about your equation. So let's move on to the types of binary operations. All right. So these are here. It is commutativity. A binary operation star is set to be commutative if a binary operation star is set S is set to be commutative and only if A star B is equal to B star A for every A comma B belongs to S. Same method. So let me check one example for that. 1 plus 2 is equal to 3 and order change 2 plus 1 is equal to 3. These both results are 3 only. So when you change the order also, if you are getting same method, then that is called as commutativity. So how it is for whole numbers, natural numbers, like that method only for this also. Let's we move on to the associativity. Same method only again. A binary operation star is set S is said to be associative if A star B star C is equal to A star B star C for every A comma B comma C belongs to S. Same method. Your identity element for binary operation also A star E is equal to A star A is equal to A for every A belongs to S. Here E is nothing but identity element. In our whole numbers and those all you'll find A into 1, 1 into A is equal to A. In same method here also A star E star A is equal to A. Alright, let's move on to the next. This is one of the theorem. If an identity element of a binary operation in a set exists, then it is unique. So if any identity element of a binary operation is exists in a set, that should be the unique, that we have to prove. Let we think two elements, two identity elements are there, then we can solve it. So let E and E star are identity elements. E and E star are identity element. So then what is happens, just let me think here. First, E is an identity element, and just use your previously we learned that identity you can use. So then E star E dash is equal to E dash. Here E is identity element multiplied with any element, that only you will get. Same method E star E also you are going to get as a E dash according to the property of identity which we learned in the last point. So he star E dash is equal to, so he is your identity element. So same method, whichever it is E dash. So let's move on to the next. So same method reversely you do now. So E dash E E dash star E is equal to E. Here E dash is now identity element. E star E dash is equal to E. So give equation number 1, give equation number 2 from 1 and 2. So E dash is equal to E. So that means only possible. So this is only the one element is possible, so that it is unique. So if so now let's move on to the inverse element. If if A comma B belongs to S, then A star B is equal to B star A is equal to E. E is nothing but here identity element, means that the operation is commutative operation equal to the identity element, then B is called as inverse of A. So otherwise we can say that B is equal to inverse. This is about inverse element. Let's move on to the next topic. So this you are not, you remember here. So E star E is equal to E star E is equal to E. Here E is nothing but identity function having a binary operation with the identity function itself. Then you will get as identity function only. Remember this for your exam. Next we are moving to the next one. We are moving to the next theorem. Just you can observe here, inverse of any invertible element with respect to an associative operation is unique. So proof is that let star be a binary operation in a set S which have identity element E. Let A is an inverse element of S, then let B and C are inverse element of A under S. Under S is possible. So then what is going to be happen? So let the meaning of this whole statement is this: B is equal to C is equal to A inverse. That is, let B and C are inverse element of A under S. So inverse element of A is nothing but A. B is equal to C is equal to A inverse. So now B star A C star A is equal to, here you just observe carefully, here we are going to the associated to B star C star A. So another we can write it as that is B star A star C. Okay, in a second we took as B star A, so that I'm going for the first also B star A star C. So now what I can write here, just observe carefully here, this is equal to B star as it is, and then I can write in the bracket one. First you need to complete there A as it is, you can write, and the C means what do you know, A inverse. So just substitute it now. So now in the bracket we are going to write piece of, let me take piece of chalk. Right, I'm going to that now. So now I can write here, it is A star C is nothing but A inverse. So after that, that is equal to, you'll write as B star A cross A inverse is nothing but E. So that we can write B star E. So now same method can we apply for this. This is again B is nothing but, you know, that A inverse, you can write A inverse star A bracket cross C is equal to A inverse star A is nothing but E star C. So now what do you know, B star E is nothing but, that is, we can write it as B. At the same manner, E star C we can write it as C. So that is about that, and let's move on to that. So now from this we proved that from the A inverse B is equal to C, we proved. So we can write, see here again I'm saying that from the A inverse we proved that B is equal to C, so that this associative operation is unique. So you found that associative operation is unique. So unique is nothing but that both are equal to the A inverse. That is only one identity, one invertible element is there, that is A inverse. Because you observe that yeah, respect to A associative operation is unique. Okay, once again we'll recall it. Let star be a binary operation in a set S which have identity element A. Then let A is an inverse element of S, and B and C are inverse element of A and S is possible. B is equal to C is equal to A inverse. Then here B is equal, by using A inverse, prove that A B is equal to C here when you are writing in the associative property. Let we see in that place now. And so here B cross A cross B star A star C and B star A star C. So in the brackets, whichever the C and B are there, substitute A inverse. So now here A inverse substituted in this bracket. So A star A inverse is nothing but E. So B cross E. So you could not find that, but that is nothing but B star E is nothing but B, and same method here, B plus we substituted A inverse in star A is nothing but E. So E star C is nothing but C. So that associative operation is unique. So this is about your theorem. So let's move on to the, if you have any doubts you can ask in the YouTube comment section. Let's move on to the another topic. So another topic is addition and multiplication operations in modulo system. So what is that? If A and B are integers and A minus B is positive integer divisible by M is nothing but A modulo, then A is congruent to B modulo M is denoted by a symbol and read as A is congruent to the modulo M. So how we'll write that? A is congruent to the three lines is congruent B modulo M, that implies so M is divided with A minus B, means whichever A minus B you get, that is divided with M. So like we check some examples. 18 congruent to the 6 modulo 2, so that means 18 minus 6. What is 18 minus 6? You will get, let me check, 18 minus 6 is equal to 12. So 12 is divisible by 2. Modulo here is 2, so that it is divisible by 2. Then we can say it is possible to divide. So that 18 is modulo to 6. Same method, let we take say another one, minus 14 is congruent to the 6. Let modulo 4, then minus 14 minus 6 is nothing but minus 20. This minus 20 is divisible by modulo 4. So means it is divisible by 4. 4 5s are 20, so that it is possible. So we can say this is minus 14 is congruent to 6 modulo 4. So that is about that, and let's move on to another topic, composition table for a finite set. So this is one of the example to understand that S is equal to 1 comma omega square. This is not x, it is into, where omega is a cube root of unity. Let we first draw the table into 1 omega square. Then just observe how I am drawing the table. So here what is the given, where omega is the cube root of unity. So what we can do here, it is just observe now in this table, 1 into 1 1, 1 into omega 1 1 into omega square. But if it comes as a omega cube, then what we need to do, omega power 4, what we need to do. So let me write here so that you can understand how to solve that. So now omega cube is nothing but 1. Why? Because here they written cube root of unity. So now omega power 4 we can write as omega cube into omega, that is nothing but 1 into omega, that is nothing but omega. Same method, omega power 5 we can write as omega cube into omega square, that is 1 into omega square is nothing but omega square. So now let's we move on to the table, 1 into omega and omega into omega square. Omega into omega square is nothing but omega cube, that means 1. So now omega square into 1 omega square into omega cube, that is nothing but 1. Omega square into omega square is nothing but, it is, you are observed, we found it as omega, so that write it as omega. So that is about your composition table for this example. So let's move on to the another example, which is about addition. So you know that multiplication identity is 1 and additive identity is 0. Here plus 4 is there. Let me draw one more table here so that you can understand clearly this. So once again, just observe how I'll draw the table. So whichever come after given plus 4 written first, and remaining all the 0 1 2 3 I written this side and that side. So because that 2 need to be added, so let me draw properly this table, then I'll move on to the solution. Okay, so now what we'll do, 0 plus 0 0, 0 plus 1 1, 0 plus 2 2, 0 plus 3 3, and 1 plus 0 1, it is not 0. So then 1 plus 1 2, 1 plus 2 3, 1 plus 3 4, 4 means what do you know, 0 now here. So if it is multiplication 1, addition means you have to write only 0. So now 2 plus 0 2, 2 plus 1 3, 2 plus 2 4, 4 means 0. 2 plus 3 5, 4 plus 1 means that is 4 is 0, 0 plus 1 is nothing but 1. How it is, just once again observe, 5 is equal to 4 plus 1 will write, 4 is 0 plus 1, that is nothing but 1. So now let's move on to next, 3 plus 0 3, 3 plus 1 4 means 0, 3 plus 2 5 means 1. So and 3 plus 3 6 means 2. So this is about your addition table, composition table for a finite set. So this all about your total introduction of binary operations. Here again we can recall it. What is binary operation? Binary operation is nothing but, so if any operation plus minus into whichever it is applied to the two operands, that is a comma b, then we are going to get binary operations. So we are going to call that as a binary operation. And this is about, I tried my possible, all the definitions I tried to give it to you all. And if you have any doubts, you can comment on the YouTube session comments, so that I can help you all. So may God bless you all.